What I'd like to do now is take a look at using the camera in processing, how to load video in from some camera source that's attached to your laptop, for example, or built into your computer. So using the camera in processing is pretty straightforward. We use a object called capture, a class called capture, which has a bunch of methods including list, which lists the cameras available, read, which reads in a frame of video from a camera, start and stop, which fairly self-explanatory, will start reading a stream of video from a camera and stop it. So we can take a look at the video sketch to see how this works. In order to make this work, I'm going to shut down my video sketch just so we can not have a conflict with the camera. So again, we're using the classes in the processing.video library. Up here we declare an instance of a capture, we declare a variable of type capture. And in our setup method, we set up our processing window, and then we create an instance of the capture method. Again, we pass in a reference to this sketch using the this keyword. Not super important for us to worry about exactly what that means if you're not too sure. And we pass in the width and the height of the video stream we want to access. So I should check. I think that actually scales the height of the video. I think it scales the video coming from the camera. So obviously your camera will have kind of a native resolution that it will be feeding in. And depending what variables you pass into width and height, that native resolution will be sort of scaled up or scaled down to fit width and height. I'm not 100% sure on that, but if I'm incorrect, please someone can correct me in the comments underneath the video. And after we've set up the capture object, we simply call the start method to start streaming video from the camera. Then in our draw method, we simply check, is there a new frame of video available from our camera? If there is, we read it. The reason we check, I suppose, is because a draw method might be called, say, 60 frames a second, but a video camera might only be supplying a frame of video, say, once every 30. It might be supplying a frame of video sort of 30 times a second or less. So that's why we check to see if there is a new frame of video available. If there is, we read it in. And finally, we draw the frame of video on the screen using the image method, passing in our instance of the capture object to that. So hopefully that's fairly straightforward. And if we run this, then we get the live stream of video from our camera. So hopefully that is fairly straightforward. Let's kill that. And again, because we are getting, each frame of video is an image. So just as it was when we were loading frames of video from a movie file, where we can manipulate the pixels and do interesting things, apply filters and all that kind of stuff to the video, which is quite fun. So if I open up, for example, Mirror, and let me run it first to show you what it does. Creates kind of an interesting pixelation effect. A bit hard to tell exactly what's going on there from watching me move around, but it's certainly intriguing. You can certainly see that it's based on me moving around in front of the camera, but it's probably a bit hard to tell exactly what it's doing. Let's take a look. We can see that we're setting up some variables here: cell size, the number of cells in the grid. And actually, let's just also look at the comment up here, which from Daniel Schiffman, some of whose videos we've been watching in this subject, because he explains to us very succinctly what is going on. And he's saying that each pixel from the video source is drawn as a rectangle, and the rotation of that rectangle is based on the brightness of the pixel. Yeah, so breaking our video source down into individual pixels, and we're drawing each pixel as a rectangle using rect, but we're rotating that rectangle based on how bright the pixel is. So we're we're specifying the size of the cells that we're breaking the image down into. We're saying how many columns and rows we're going to break it into. And look, I don't think I will talk through this code right now in the video. I think we can talk through this in the lab, but hopefully it's fairly self-explanatory. There's nothing really particularly more complicated about this than there is about other image manipulation sketches we've looked at previously. I guess what's more interesting about this is not so much how it is done, but the concept of accessing each pixel of the video and manipulating it and then rendering it in a different way based on sort of real-time analysis. So again, we're just something that you can do because each frame of video is an image. So that was mirror 2 is very similar, except this time we are drawing each pixel in a video as a rectangle with the size based on the brightness. So previously it was the rotation being affected by brightness. This time it's the size of the rectangles. So we should see when we run this that brighter pixels in the source image draw larger rectangles. So sort of where my face and hand is here is obviously brighter than my jacket, which is quite dark color. So there's almost no rectangles down here on my jacket, which you probably can't see I'm pointing to. And then sort of up where my face and head is, the rectangles are a lot larger. So again, hopefully from looking at this example, you could kind of get ideas for lots of different ways that you could manipulate live video and make interesting looking effects using fairly simple algorithms that analyze the value of pixels in the stream of video coming in. Where this also gets quite interesting, this leads us sort of into real-time video analysis. And so we've, in the subject, played with the Kinect camera previously. And you would obviously recall that the Kinect camera, tracks the movement of people. And where we're going with this video analysis, where we're going with this sort of video manipulation at the moment is towards the kinds of coding you would do if you were doing real-time video analysis to, for example, track the movement of a body against a fixed background and things like that. So what we can do quite easily is do things like, say, track the brightest pixel in an image. Track the brightest pixel in a series of video images, or we can even subtract background out of the video, so that, in other words, things that are not moving in a video frame can be kind of ignored, subtracted, and we'll only focus on pixel areas that are moving or that are different to that background. Let's take a quick look at a couple of examples where we're doing that. Brightness tracking is here. Let's take a quick look. So this stuff shouldn't be anything particularly new here in our setup method. Just setting up our our capture object, setting up access to the video camera on the laptop, starting off the video stream, a couple of other things there to tidy things up. Let me run it again before we get into looking at the code. The details of the code are not so important. But what you can see there is a big yellow circle drawn on where the brightest pixel in the image is. And by default, it's kind of right in the middle of my shiny head. And you can see as if I move my hand into the light and try and make it the brightest part of the image, then the circle starts tracking that. So even from, you can imagine if I had, for example, a torch or a small light in my hand, we could use an algorithm like this to track the movement of that light, especially if we have a nice bright background and we have some control over the lighting. So I guess we probably don't really need to look in detail at the code. I think it would just get confusing for me to try and work through it and explain it to you. But it's, and if you open the code and have a look, it's all very well commented. This, by the way, is an example from Goal 11. I think is one of the examples that comes with processing. But essentially, we're looping through every pixel in the current frame of video, checking how bright it is. If it's brighter than any of the previous values that we've got, we sort of recall the number, the number of this pixel. And if it's not brighter, we don't do anything. And we keep doing that until by the time we get to the end of the pixel buffer, we will have identified the location of the brightest pixel, and then we simply draw a nice yellow circle around that pixel. So that's one sort of simple image analysis technique you can use. Let's also take a quick look at background subtraction. This is also an example from Goal 11, whose work we've looked at in previous weeks. Let me run the code to show you how it works. So when I run the code, you'll see there is the usual video window that pops up. What happens if I duck out of the frame as much as I can and hit the spacebar and then move back into the frame again? When I hit the spacebar, the sketch sort of recorded the image that was there in the background behind me. And what it does when it's running, it looks at the incoming stream of video and compares each pixel in the incoming stream of video with the pixel in the background image that it took a snapshot of. And it subtracts the value, the RGB values of each pixel in the incoming stream from the value of the pixels in the background that we took a snapshot of. And if you think about it, the effect of this is to where the background, where the incoming video stream and the snapshot image, where the pixels corresponding pixels in those are the same value, we'll end up with a pixel with a zero pixel value. Sorry, a pixel with a value of 0, i.e. black. And it's only where the pixels are different in the incoming video stream and the snapshot background image that we will see anything other than black. So as you can see, as I'm moving around here, we're seeing movement, and where the background is in the image, it's kind of been subtracted away. We're seeing just blackness. So let's have a look at the code to see what's going on here. I don't really want to look at it in detail, but essentially we're going through and getting each frame of video again. We're loading the pixel buffer, as we've done previously, and then we're getting the current RGB values out of the incoming video stream, and also the RGB values of the background snapshot image. And we're calculating the difference between the current R value and the background R value, and likewise for green and blue. And we're storing those. So we're subtracting the background red value of each pixel from the current red value of each pixel, and storing that in this diff R, diff G, diff B variables here. And then we're drawing all the pixel. Basically, we're drawing the difference values. We're drawing an image where all the pixel values are the difference between the current red, green, blue and the background red, green, blue pixels. I'm not sure I completely understand my own explanation of that. And it looks like I've accidentally taken another snapshot there. Let me move out of frame again and demonstrate once more how this works. I hit the spacebar, we take a background snapshot image. Where the current stream of video coming in is the same as the background image, we will see black. Where they're different, we will see the difference between the pixels in the current image and the background image. So that's, and you can see the kind of, you can see visually the kind of effect you get. And I accidentally just hit a key again just then. But background subtraction is quite a useful method. It's often a method that's used prior to doing image tracking, where you want the you want to ignore the background and you want to only concentrate on something which is moving, like a person that's moving in front of a still background. So that's why I kind of highlighted there, as well as just to point out it's another effect you can get by messing around with the pixel buffer and manipulating the pixel values of that.